Hello everybody. In this presentation I want to say a few things about symbol-based knowledge representation. And as you can guess from the title, there's going to be a second part coming up soon. Today we want to have a look at kinds of knowledge. We're going to look at the use of logic, frames, and semantic nets to represent knowledge. Notice I call this thing symbol-based knowledge representation. We already looked at neural networks and we dipped our toes a little bit in the pool of understanding of how neural networks represent knowledge. And we'll go back to that very, very soon to compare and contrast the symbol-based and the neural network-based of knowledge representation. So let's have a look then at these three kinds of knowledge representation. But before we do that, let's talk about kinds of knowledge. So we can distinguish between many different kinds of knowledge. Two key ones are certainly conceptual knowledge, typically knowledge of facts and the way the world behaves. So for example, we may know that birds can fly. We know there are exceptions to this thing, but by and large, birds can fly, right? Facts. We may know what a chair looks like. We may know what a bicycle looks like. Then there's procedural knowledge. Sometimes this is called skills. So here's an example: playing the piano, playing the violin, programming, right? Developing software. These are skills that you have to practice, and you only get good at them once you do them for a while. So somebody can tell you, yeah, in order to play this piano concerto, hit these keys, but that doesn't mean that you can sort of like play the piano in the sense that people might appreciate listening to you playing the piano. So it's a skill, riding a bicycle, right? We kind of fall off a couple of times until we get the hang of it. There are many other knowledges. Here's an example: emotional knowledge, right? The knowledge of how to interact with others, how to make people feel comfortable, how to play nice with others. So lots of knowledge. Just want to point that out. What we will be doing here is we'll be focusing on conceptual knowledge, the sort of stuff that we might find on Jeopardy, on IBM Watson, and those sorts of things. So let's start out with the use of logic to represent knowledge. And the reason I'm doing this is because I just introduced logic last week. We looked at propositional predicate logic, and I sort of like portrayed it a little bit as sort of like the atom of knowledge representation, the most fundamental way of doing this thing. It also turns out this was one of the earliest way in which people, the earliest formalism that people used to represent knowledge. What we typically are looking at is conjunctive normal form. I linked up some of these links also on our page. We will, I briefly want to mention that one of the early planners was by a person called Green, who used theorem proving, conjunctive normal form, and the resolution rule to develop plans to solve problems, simple problems. This is the resolution theorem proving approach that he used. Since I'm over here, there are some other planners that people used very early on that's like a primarily logic-based. Strips is one of them. Here is the original paper, and here is the Wikipedia entry. Well, the Wikipedia entry for it. So let's go back though to our presentation. So here's an example of how we might use conjunctive normal form to represent knowledge. Tweety is a bird, and Tweety can fly. Tweety has wings. A is a block. A is on B. Has Tweety wings. So that's a little bit duplicate, so we probably don't want to do that. Maybe we'll sort of say color. Tweety is yellow. So what's the problem with this thing? Again, people were able to successfully use this thing to develop simple plans in the blocks world, something we'll look at presently. There's just no order to the information or knowledge base, right? So this poses a serious efficiency problem. If we sort of like take everything we know and throw it in a database or into a flat file, which it typically was, we kind of, if we want to figure out, can Tweety fly, or, if we want to solve a problem about blocks, we got to look through all this junk and find the information that we're looking for, right? That alone is a serious efficiency problem. Think about, the way we dealt with efficiency in breadth first search. We had the open and the closed list to sort of like manage duplicate states. It's a serious issue. So the way this problem is usually solved is by making what is called the closed world assumption. In it, we assume that only information that is pertinent to the problem at hand is represented in the system. So if we have a planning problem, we only talk about these two things. If we want to know something about birds, well, we may only represent these couple of things, the top two and the last one. So that certainly helps out. Now, you might imagine that while this works for what people call toy systems, some of the early systems, this doesn't really work or mirror the way people work. So a key aspect of cognition is to determine which of the information we get bombarded with is pertinent, right? Think about fake news, right? We get all this stuff and we sort of have to figure out, what's right, what's wrong. But even in the real world, when we walk down, the quad, you want to avoid bumping into people, avoid bumping into immovable objects, those sorts of things. You might want to say hello to somebody you know. So we're constantly processing information and so determine what's relevant to what I'm going to be doing here next. So that's why eventually people developed frames. So frames is one way to look at them, or a key aspect of frames, to organize the data in our knowledge base around organizational units. So if we have a planning problem, we may sort of say, oh, okay, so all right, there's a table, and B is a block, and it's on the table, and A is a block, and it's on the table, and C is a block that is on A. Now notice this is just a graphical representation of some facts that I will show you in a minute. But the idea is, we're sort of saying, at some point in time, say situation S1, this situation holds, as it is portrayed in this image. So we're organizing things around things, and we're going to have in this particular example around states of the world, and I'm going to have an example later from a different one. So here is how we could represent this thing, say in Lisp or Scheme. We define state as one to consist of block A, block B, block C. A is on the table, B is on the table, C is on A. C is clear, B is clear, and the hand of the robot is empty. I didn't show the hand of the robot. So it's understood that all these items on the list are connected by the Boolean AND operator. So block A and block B and block C. So this is true about situation S1. All right. So here is an example from Prismatic, which was the dependency parser used in IBM Watson. So if we look at the following sentence, in 1921, Einstein received the Nobel Prize for his original work on the photoelectric effect. So the organizational unit in this example is our phrases that we're parsing here. So notice that we actually have two frames, and this frame 02 is being referenced from frame 01. So we have in this frame here, somebody received something, the verb. Then we have who received it, Einstein. We have named entity recognition. He's a person, a scientist. What did he receive? He received the Nobel Prize. When did he receive it? In 1921, which is a year. And for what? And so he received it. So here we reference another frame. So I don't want to get too much into the details, but the idea is that here we organize information around a sentence, right? A sentence that we parsed. In other words, a parse tree, or pertinent information from our parse tree. So the idea, not just a flat file, but organizing it so that we can later on process things efficiently. Here are some of the slots that can be used for a frame. So again, over here you see an example, and over here you see the complete slot, list of slots that can be used in the Prismatic system. I think I'm going to say this later on today too, but you can sort of like think of frames as like objects, or at least the fields of an object, right? And so you have some of these things, some of these fields that might exist, and you fill them in. Some of them you declare as null, some of them you can predefine through other means that we're going to look at later today. All right, so let's go back to then an issue that exists when we use frames, and in general when we do knowledge representation. So we'll define the frame problem now. itself, the frame problem has been solved, but there are some derivatives from the frame problem that represent key unsolved problems in AI. So let's consider the planning problem from earlier today. I have the situation S1 over here. And so what we want to do when we do planning, we need to define rules. And these rules or actions enable us to, do things to those situations to modify them. So here's a rule for moving a block. If you want to move X, you move a block, from X to Y, then we can only apply this rule if certain preconditions hold. So for example, the robot can only move move block X to Y if it holds X, if Y is clear, and if X is on some block Z. This is technically not a precondition, but we'll sort of stick it in here for now. The post condition is that X from which we move something, so think about block C. So suppose we want to move C on top of B, so move C, B, that's what we would do. That's what the semantics of this move command is. We obviously have to hold C. We don't have to pick it up yet. B has to be clear, and so C is on top of something else, in this particular example, A. So the post condition is that A is going to be clear, and C is going to be on top of B. All right, unless we say release the robot hand, we're still holding it. So what we need to do here, and this is kind of crucial, is we need to delete some information. We need to know what changed as a consequence of this action over here. So what we'll delete from our database then is that that this one over here, that C is on top of A, and that B is clear. So those are two things that we need to remove. All right, so let's see why I'm talking about all this stuff. What we have over here is we have the pre and post conditions as well as the delete list. You can have a separate add list. A lot of times the post condition is the implicit add list. So when we apply a rule, we can only do that obviously when the preconditions hold. But when the rule is applied, the following happens. We're going to create a new state. So you can just do that by cloning the existing state. So whatever we have over here, however we represent this state, we have looked at this earlier today, we're going to clone that information. All right. So it is cloned. So now we need to modify some of that information. We need everything from the post condition needs to be added to this state. So you would add these two pieces of information, again, instantiated. And then we're going to use delete list to remove item in the cloned state that held before we executed the action, but that do not hold any longer. All right. So that's how we do that. That's how we develop a new state, say S2, in which we have performed the action of moving block X, whatever we instantiate that one to the top of block Y. All right. Okay. So notice that the frame problem actually gets its name from these frames. We have this frame information, and we execute an action, and we need to know what's the new state of affairs. Now notice that a key aspect is over here. When I say move C on top of B, I don't even mention A or any other blocks that exist over here, right? So we need to know what data needs to be copied from this situation to the other one. And the way we do that is through the clone command, right? And then we clone first, and then we modify certain things. We remove some information, and we add some other information. That's what we did over here. So at this point in time, it's a very technical problem. The way we solved it is with clone and the add and the delete list. Now, it turns out that while we solved this thing, it sort of like exposed a bigger problem. And it morphed into the problem of specifying what does and does not change as a consequence of an action. So let's have a look at that. If you took 120, you may have programmed a robot to move across the floor. And if you want the robot to drive in a straight line, you program each driving wheel to turn a certain number of revolutions. And most of the time that worked out, right? But if there was, say, and we have carpet in there, but then sometimes there's plywood in there, and so there's traction, and there are traction issues, right? And so sometimes it just didn't drive in a straight line. So sometimes it did. So let's see what we can learn from this thing when it comes to planning. Now, those of you who are parts of the robotics club, you know that you have a feedback loop, right? You have sensors that sort of sense, oh, geez, I'm not exactly where I want to be, so you adjust. And so that's kind of what you want to do in modern day planning. But let's go back to exposing the frame problem that does exist. And so let's have a look at that. I call it the frame problem in the wild. So suppose you wish to program a robot arm to pick up a block from a table. So let's ask, what can go wrong? So for starters, the block may be glued to a piece of paper on which it is placed. So the block is on a piece of paper. If it is glued to it, the paper probably moves with it. So notice that suddenly we have in our post condition something that is unexpected. So in this particular example, if we sort of like embellish it a little bit and we talk about pieces of paper and glue, then we would sort of have to add something that, oh, well, geez, you know, that piece of paper is now also moved and it's probably now between C and B. All right, so we have to make that world a little bit more complex. No big deal, right? So we would have to specify anything that is glued to some object that we move, moves with it. All right, let's do that then. But what if the paper is taped to the table? What if we use duct tape, the handy woman's secret weapon? Well then, well, the paper may just tear or it may not move with the block. Depends on how strong the glues are, right? All right, so we just add another rule. We add an exception to the exception, right? Glad we talked about that. But wait a minute. What if instead of duct tape, the paper was epoxy to the table and the block was epoxy to the table? And the table is not very heavy. Or alternatively, what if we screw the block through the paper to the table with some really nice heavy-duty screws? Well, what might happen in that case? So if the table is not very heavy and the robot is strong, it might just pick up the entire table. Or, well, the robot might topple over, or it might break, or it might start smoking. So as you can imagine, this gets to be real crazy, or this could get real crazy in the real world, where we eventually end up with exceptions to the exceptions to the exceptions to the exceptions. And that's kind of like what the frame problem exposed. How do we actually represent knowledge about the real world? Things that we kind of know, or that even if there's an expectation failure, in other words, you know, we saw like, see, whoops, the robot toppled over, then we may speculate, oh, okay, I guess the table was too heavy or was glued to the, it was screwed to the floor. So we would investigate that. We have a sense of what to look for. We have the ability to speculate intelligently about the real world. And this is where common sense knowledge comes in. And that's really the problem that the frame problem exposed. Common sense is something that people have, right? We just know how the real world works. We know that if you do this, then other things might happen, or at least we're sensitized that some things may or may not happen. But instilling this stuff on a computer is a really hard problem. We can try to formalize this thing, and then we have to figure out when and what of the knowledge to invoke. It's just really hard, and this is a current problem in AI. And it's unsolved. So let's move on then to semantic networks. So semantic networks represent information in a yet more compact form than frames. Now I should tell you that once semantic networks came in, the people who maintained or developed frames took some of the ideas from semantic networks. So nowadays, if you were to sort of look at the formalism at the code, and somebody says, oh, this is a frame, somebody else may say, no, this is a semantic network. They're kind of interchangeable today. So that's all right. We want to learn from the ideas. The key contribution of semantic nets are inheritance hierarchy or ontologies. So let's have a look at an example. So this is actually from one of the early papers by Ross Quillian called Semantic Memory, and as you can tell, it was published in '68. So here's an ontology, so we know about canaries, birds, animals, fish, ostriches, sharks, and salmon. So what do we learn from this ontology? In particular, what do we know about canaries? So notice that canaries can sing and they are yellow. So this is just a very small, very compact piece of information. That's apparently all we know about canaries. But there are these inheritance. We know that a canary, or we represent that a canary is a bird. So suddenly we know that, oh, canaries are birds. So canary is a bird. And then, due to the way we process the ontologies, due to the way these are inheritance hierarchies, we now inherit from bird that it has wings. So suddenly a canary has wings, it can fly, and has feathers. And we also know that, oh, wait a minute, they're animals. They eat and breathe and have skin. But we also know that, wait a minute, a canary is not a fish, it's not a shark, it's not a salmon. Okay, so this is all information. So it's a great way to make this information very compact. So we don't have to put into canary that it's yellow, it can sing, has feathers, can fly, has wings, breathes, eats, blah, blah. It's not a shark, it's not a salmon, right? So it's much more compact to do this sort of stuff. And that's the key contribution of semantic nets. So as I said, a node in the net inherits all the information along the path to its root, and it inherits the negative information if you wish. Let's have a quick look at ostriches. So notice that it says it can't fly, but since an ostrich is a bird, it also says that we can fly. So there's a contradiction over here. So how do we resolve this contradiction? Well, the way we process these semantic nets, we sort of like take as truth whatever is closer to where we are. So in this particular example, can't fly is directly stored with ostrich, so that's what we're going to take. So that overrules this information over here. Again, it might have been that maybe there's a particular ostrich over here, and then we will sort of like in essence take the information that is closer to our node. That will overrule anything else that is further up the rule. Notice this is very similar to Java's inheritance scheme for procedures, where some procedures override others. So same idea. Now there's some semantic nets in the wild, well, not in the wild, in the real world, and a very popular one is called WordNet. So go to this thing here. This is the web browser, and I saw like simply typed in canary. And so here's some information. And so you know that it's any of several finches, so you can type in finches. And so go up the inheritance hierarchy in semantic nets. Alrighty, folks, that's it for representing conceptual knowledge. And so tomorrow we're going to have a look at some other ways of representing knowledge. I will see you then. Bye.